Let's start the stream. The text is out of bounds. Yeah, need to fix that later. Let me go to my desktop view. Yeah. Finally, we're starting with a hacking stream. Hope this goes well. I will be addressing memory layouts and such today, so don't worry about that. I'm going from the basics, so I understand how memory layouts work first, then start getting into assembly. Then I will work a bit on, let me think here, reverse engineering, then maybe go to web, forensics, and so on. I will go through mostly everything I have an interest in. If someone in the chat suggests something, I probably will hear them out and see if I can do it as well. Hardware hacking might happen in a distant future, but I'm not sure about that, since I would need a camera and such, and maybe an Arduino, but that I can manage. I will check that, and yeah, let's get this started. So here, as you can see, we have a memory layout of C programs page, just so we can know how C programs work at first. Afterwards, we're going through Windows, Linux, and I will be drawing the diagrams and so on. So stick with me on this. So the typical memory representation of C program consists of the following sections: text segment, initialized data segment, uninitialized can't speak today. Uninitialized data segment, stack, and heap. So typically here we have a small image about this. Let me even copy image. Let me paste it here if I can. No, I can't. Mask. Can't I add images here? New, edit data, view, range, extras, so on. Entity, flowchart. Yeah, I don't think I can. Okay, let's do it anyway without importing the image here. Okay, so what is the text segment? The text segment, also known as code segment or simply as text, is one of the sections of the program in an object file or in memory which contains executable instructions. As a memory region, a text segment may be placed below the heap or stack in order to prevent heaps and stack overflows from overwriting it. Okay, let's do this. Pull this over, this here, open this up. A quick view of my desktop there. Shouldn't have happened, but what can we do, right? Okay, let me start drawing. I'm horrible at this kind of stuff, so forgive me for that. Let me see. I would love to have some better flowcharts, but yeah, a box will need to let me decent size here. But yeah, let me get rid of this notice as well. Close this one. Everything else should be good. Yeah, everything else is good. Let me open this really quick. Just take a look here. Yeah, pretty much. Okay, let's start drawing this then. Okay, we will have lines going through this. Here, here, and here. So it's a straight line. So yeah, let's go on with this. If I had some text here, text node, okay, executable code. After the stream, I will be providing everything I have worked on my Discord, so join me if you can. The link is up top. Also, we have my Twitter there, where I mostly announce streams, but if everything goes well, maybe I start posting there as well my insights and so on, depending on how I feel. So yeah, let's keep working then. Okay, so it will be placed below the heap and stack for prevent overwriting. Okay, so heap overflows and stack overflows are a thing already. These are bugs where we can exploit the code and overwrite a section of it, so we can simply execute what we want. But okay, nothing big there, nothing that is known to the major public yet. Okay, let's keep on going. Okay, initialize data segment. Initialized data segment, usually called simply by the data segment. A data segment is a portion of virtual address space of a program which contains the global variables and static variables that are initialized by the programmer. Note that data segment is not read-only, since the values of the variables can be altered at runtime. The segment can be further classified into initialized read-only area and initialized read-write area. For instance, the global string defined by char as hello world in C and a C statement like in debug equals 1 outside the main, i.e. an example global would be start in initialized read-write area. The global C statement like const char asterisk string hello world makes the string literal hello world to be start initialized read-only area and the character pointer variable string in the initialized read-write area. Static int I10 will be start in data segment and global int I equals 10 will also be start in the data segment. Okay, our text node. Let's go on with this. Global and static data. Expand this a bit. One static data. Read only. Read dash write. I don't know how to type. Read only. Read write. So yeah. Let me take this. Get it lower. A little bit more. Here should be good. Let's bring this down now. This way down. Copy this here. Paste it. There. Okay. So our memory diagram is starting to look nice. We can see that and already kind of understand what is happening here. I'm trying to create a model for myself. So if something isn't clear, let me know. I will try to fix it later and have it all done for you guys. Okay. Let's take a look. Think here. Okay. So uninitialized data segment, often called the BSS segment, named after an ancient assembler operator that stood for block started by symbol. Data in this segment is initialized by the kernel to arithmetic 0 before the program starts executing. Initialized data starts at the end of the data segment and contains all global variables and static variables that are initialized to 0 or do not have explicit initialization. Source code. For instance, a variable declared static int I would be contained in the BSS segment. Okay, so this is wrong. Initialized global. Copy the name from here, so my writing is at least good here. Okay, no, completely. Okay, initialized global and static data. Okay, so let's do this here. Up. Okay, this could be a bit. Remember, all of these segments should be dynamic, depending on code and on how much is in them. So yeah, please have that in mind. Block started by symbol. Block started by symbol. BSS. and I'm typing like banana. In initialized global and static var data. Okay, so we have the BSS. It will have initialized global and static data. Same thing as before. Let me actually bring this up. No, I didn't want a text node there. Okay, up here, bring this up, bring this down. Okay, leave initialized with 0 or not explicitly initialized in code. Let me use the square bracket here so we know this is a client small explanation. Okay, let's go on with it then. Okay, we have the stack and the heap now. Let's see how this works. Okay, first, here comes the first difference. The heap starts from the bottom up and is the fifth element. The stack starts from the top down. So stack overflows are kind of more common, not actually, but yeah, if you can overflow the stack, you could override the uninitialized data and initialized data and even the heap, but you would need a lot of text and probably your program would break. Usually you do a stack overflow to hit the heap, and a heap overflow could be used to alter environment variables or even maybe the stack. So yeah, we can look into this further. I might be talking a lot of nonsense here, so bear with me. I'm sorry if I'm not being true to the thing. If anyone knows better than me, please let me know. I would like to know better. Come on, I want just this line. And bring it down a few pixels. I will push this up. Okay. So here we start having a text node for the stack. Up top. Okay, stack. And it went right. Didn't want to click there. What just happened? Okay, forget about it. Okay, stack. The stack area traditionally adjoined the heap area and grew to the opposite direction. When the stack pointer met the heap pointer, free memory was exhausted. With modern large address spaces and virtual memory techniques, they may be placed almost anywhere, but they still typically grow opposite directions. So this means we have the heap and the stack growing into each other in a mostly old solution of this. Not really old, but a more archaic solution, I would say. And in modern memory spaces, we have them placed anywhere in memory, so they wouldn't grow into each other, but they still grow in opposite directions. Stack grows from high to low, heap from low to high. So yeah, if we have control of lower addresses, we could write into the heap and keep growing the heap. And if we go from high to low, if we want to hit something in a lower address, we could go from the stack down. So yeah, sorry if I'm wrong here again. I really don't know what I'm talking about here. I am graduating in computer science, but this is way out of my league already. I didn't learn this properly, so forgive me for that. The stack area contains the program stack. LIFO list. LIFO is last in first out structure, typically located in the higher parts of memory. On the standard PC x86 computer architecture, it grows towards address 0. On some other architectures, it grows the opposite direction. The stack pointer register tracks Stack pointer register tracks the top of the stack. It is adjusted each time a value is pushed onto the stack. The set of values pushed for one function call is termed a stack frame. A stack frame consists at minimum of a return address. Okay, so stack. Let me. What the hell? No. Oh no, no! I didn't want this. Come on. Sorry for my inability here. I'm really bad at stuff like this. Stack, last in, first out, data structure. Okay, we know what the stack is now. It has less than first out, so it will start the first item that is pushed into the stack will stay there for the longest, and the last item can be popped off. So imagine a stack like a stack of coins. In computers, they are on the ceiling, so don't get the metaphor doesn't work as well. But imagine you had a stack of coins. Every time you add something on top, you get the last coin is hard to remove since it would just blow the whole stack. And if you remove the first one, then you have anything. Okay, contains the LIFO. Okay, a stack pointer register tracks the top of the stack. It is adjusted each time a value is pushed onto the stack. The set of values pushed for one function call is termed a stack frame. A stack frame consists at minimum of a return address. Okay. Let's actually let me do something else here. This heading. Let's do this. Stack frame. Okay. Stack frame is a pointer, and the set of values is termed a stack frame. It is a set of values pushed to the stack that for one function call. Okay, a stack frame. So we have that. Also, come on. I'm not really that bad at doing stuff. Okay, here as well. So we have the stack pointer to the address of the top of the stack. Okay, so we have two terms here. That's nice to know. Stacks where automatic variables are stored along with information that is saved each time a function is called. Each time a function is called, the address of where to return to and a certain information about the caller's environment, such as some of the machine registers, are saved on the stack. The newly called function then allocates room on the stack for its automatic and temporary variables. This is how recursive functions in C can work. Each time a recursive function calls itself, a new stack frame is used, so one set of variables doesn't interfere with the variables from another instance of a function. So in C, we have this working in a way where we save every information about the previous function, at least the ones we need to, like the registers in that function, and then we go on. Also in the stack there are automatic variables stored. So I think that means that here is where we have the variables we create in our code that aren't global or static. So yeah, and we have the colors environment are saved on the stack. Okay, let me add one more card here. saved on stack. Automatic variables. Also, we save colors in environment and return address. Okay. There's environment machine registers and return address. Okay. Sorry for my English. I am not natively speaking English, so I feel a lot about that. So sorry. Mostly. Okay, so here we have our stack. Our structure. Okay, isn't there a way to add? Let me see here. I think I have a solution for my problems. Okay, we do this. We send to back. We pull all of these down a bit. Okay. I think this should be a no. I just say no. Let me get this all down. Still not enough space, huh? Let me put it even more down then. Okay. Let me have a text here. Text node here. Stack. Let's do this. 36. Like this. Bad at judging sizes, so the stack. Okay, am I right in this word? Yes, I am. So okay, let's go to the last section here, the heap. Actually, let me get a line here where I can hit those. Here, set it up. Okay. Copy it, paste it here as well. And now I need some arrows. This should work. Arrow. Can I rotate this? Delete it. I need a straight arrow. Please, people. Where is a straight up arrow? Okay. Come on. Like this. Now I reduce it a bit. Oh, come on. I just made a square. This. Here. And the down arrow. That should be. Oh, it's kind of off. There. Up. Okay, let me shrink it a bit as well and put it here. Okay, we have the stack growing down, the heap growing up. So let's now let's get this rolling again. And here we have the heap. Now let's see how the heap works. Heap is a segment where dynamic memory allocation usually takes place. Okay, already something that we don't know. Okay, the heap area begins at the end of the BSS segment and grows to larger addresses from there. The heap area is managed by malloc, realloc, and free, which may use the BRK and SBRK system calls to adjust its size. Note that the use of BRK, SBRK in a single heap area is not required to fulfill the contract of malloc, realloc, and free. They may also be implemented using mmap to reserve potentially non-contiguous regions of virtual memory into process, virtual address space. The heap area is shared by all shared libraries and dynamically loaded modules in a process. So, okay. Let's go for it then. Okay, memory allocation. Okay, and here we have a small notice that reads shared by all libraries and all my shared by all shared libraries and you see dynamically loaded modules. Okay, this became a bit big, so let me remove it here a bit. These two go up, down please. So we have here our heap. Okay, now let's go to the next section. Okay, we have up top here. Okay, let's add this as well. Branch, subtopic, vision. Okay, I want a branch. Okay, let's do this corner. Low addresses. Low address. Okay, another one of those branches. Our stack here needs to go to the side. Okay, now it's up. Okay. High address. Okay. Our notice should be here. Okay. Okay. I didn't do this well. Okay. Yep. Okay. Let's go to the next thing here. Oh, my frames. Sorry about the frames, people. It's dropping a lot here. As always, really sorry. Can't do much about it. My connection is bad. Nothing I can do about it currently. Here. Now I arrow a bit, and that's it. Then we have this one here. Properly. Okay. Shrink it a bit. Okay. Now I will shrink it here so we have a better view of it. Okay. And then up top we have another arrow that should be aligned with these ones. Okay. Here. This, and then I shrink it and like this. Okay. Like double click here. No. Okay, we have all of the arrows needed here. Let's add some text. No, not the title. A text. 2, 3 texts. Notes. Okay, up here. Let's see. Comment, line, arguments, and variables. Actually, I already talked a lot of nonsense, right? So sorry about that. The environment variables are up top, so the stack would never manipulate them, but we could mess with allocated memory for our shared libraries and dynamically loaded modules. So depending on what's there, we could do that, but from what I remember, mostly what you do when hitting a stack is when you get a stack overflow, you can get a stack pointer to change. So that would be it, what we could do. or even just ignore the whole heap if it's small enough, or figure out exactly what's written there and write it exactly as is, and change something like a static variable in the read-only section that was initialized later, or even a initialized global and static data in the read-only / read-write area way down there if we can, but it would be hard, very hard, because we would need to know everything between it and be able to just replicate it perfectly. But yeah, we probably will just stay with a stack pointer change that will fix everything we need. Yeah. So, as I'm still learning, a lot of bullshit from my end. Okay, let's get the next text node. Not like this. This initialized to 0, 0 at execution, like this. Okay, and the last text node have, if I can click, would go here. What the hell? This one, and read from program file by execution. Okay. So these are some interesting things we can use in programming as well. So knowing how the addresses are placed would let us prevent some things like probably identify if we will have a stack overflow, a heap overflow, there's buffer overflows, and a lot of these things. But yeah, we will need to check this. Let's keep going on this page, check what they have here. Check the following simple C program. Okay, you see memory layout.c, just this. Okay, it returns just 0, and so memory layout, size, memory layout. Okay, we can see the sizes using the GCC compiler if we have the source code, so that's very interesting. So we have here the text area, the code, will have 960 of size. I am assuming this is bytes or bits, not sure. Data is 248, since there's not much. There's mostly the main here. No, I'm lying here, sorry. Nothing much here, maybe from stdio.h, standard input and output, not sure. The BSS is 8, then we have deck 1216, hex 4C0, and file name memory layout. Okay. Oh, this is the file, yeah. The file name is the file we compiled. Here, memory layout. Let us add one global variable in the program. Now check the size of BSS, highlighted in red color. The BSS changed. It was an int. An int is not initialized here, but ints are 4 bytes in size, if I'm not mistaken. So this should be in bytes, everything. Let us add one static variable, which is also stored in the BSS, static int I, not initialized. Again, added 4 because of sizing of ints. Let us initialize the static variable, which will then be stored in data segment.ds. Okay, we initialized it with 100 for the static variable. So it starts in data now. The data upped in 4, the BSS in 12. Okay. Let us initialize the global variable, which will then be stored in data segment. Data segment, ds. Then you add it here. It reduced to 8 since we removed it from the BSS and added it to the data. The data upped in 4 because of sizing. Okay, here we have some sources. Okay. Okay, now I'm interested in sizes. C variable type sizes. Okay. Okay, here we have C data types inside with sizes. Let me add it quick and dirty here. Okay. this here. So yeah, data types. We have basic data types, derived data types, information data types, and void data type. Okay, we have data types. Int, char, float, and double are. Okay, let me annotate all of this. Isn't there tables? Oh, we have tables. Nice. I don't care. Let me put this up here. Delete this. Okay. I will delete this last row. So this one will become type, and this one data type. What I can do here? Basic. What just happened? I heard a ping. Oh. Shut up, I don't care. Can I close this? No? I hate this chat who does things from Zendesk. Can I disable them? Yeah, some at least. So it doesn't bother me again. Okay, for basic, we have int, char, float, and double. So, int, char, float, and double. Integers, characters, floating point numbers, and doubles. Doubles are bigger floating points. Not correctly, but yeah. And floats have 6 decimal places, doubles have 15, so they are a bit bigger in decimal places only. So yeah. So we have the basic data types down here with all their storage sizes. Yay. Okay. Okay. Come here. Derived. We have array, pointer, structure, and union. Okay, now I am confused. I don't know what an union is in C. Sorry about that. My knowledge is quite not that much in C, but yeah, arrays, as always, a array of data, like a list of 45 items maybe can be stored in an array. If it can be bidimensional, I guess. You could have that. Yeah. We have pointers. Pointers are variables that contain addresses to which they point. So you could point a pointer to a function, a variable, or anything you want actually. It will have an address in itself, so it can be used to change what variable you are accessing and such things. We have structures that are kind of arrays that have different types of how can I say this? Different types of data inside them. I would say structures are a type of object, but that is taking it too far. It's not an object, but it's more like a version of a data type that can hold multiple data types. Hey, Yugen, it's going well. I'm a bit confused here because I'm not that versed in C, but yeah, I am drawing up here some resources for myself, how the C stack is working. Here we have some stack related information at the side, and down here I'm annotating the data type sizes so I know how much each has, so I can maybe in the future use this for some hacking or for some development. Who knows, right? So yeah, we'll extend this a bit down. Okay, let me see. Oh, unsafe changes. Yeah, no one cares. How do I add more? I am not versed in this at all. By the way, how are you doing? Let me see. Insert text line. There's line. Ah. Oh, I can't. I don't know anything. God. I really need to become better at this. Maybe at the side panel? Text, range, check. horizontal, coupling size. Busy day, but doing fine. Yeah, nice to hear. God, I'm bad at these things. Says children, no. It's resizing anyway. Horrible. No. How did I do this before? We expand this. Like this. On these two and place them. Then. No. And copy these two then. This. I select then this one down here. Oh, come on! I'm that bad, as you can see. Okay, come on, why did you create this? Okay, I actually don't know how to use this program. Can I add lines here at least? Front, back, edit data. ID, no. Cut, duplicate, set it as default style. Text, arrange. Yeah, I'm lost here at all. Okay, let's jump back into this. Remove this one. This table. Can I paste just it? No. Right. I know this exists, but yeah. These format panel, outline, layers, scratchpad, shapes, grid, shadow, connection points, arrange. Okay, insert, rectangle, ellipsis, text, image, template. Wait. No, thank you. Okay, let me just get this over with. Okay, so we have the data types here. Get back into the talking at least. So the basic data types: char, unsigned char, and signed char. They go from a char goes from -128 to 127, or 0 to 255. It can be unsigned or signed. I don't actually know why you would use a signed char right now. I know unsigned chars are used for ASCII, so we can type. But unsigned, a signed char, I'm not sure what that would do for me. Okay, int, we go from -32,768 to 32,767. It has 2 bytes. What? 2 bytes? But that's wrong. It occupies 4. Okay, this side is not good. Let me check this one out then. 1, 1. Oh, here, 2 or 4. Okay. Now we have our better table. And int can be, yeah, a lot of stuff. Okay, let me see. Can I paste this? Yeah, I can. So yeah. I need to organize this all for myself later. God. Don't need the translation actually. Yeah, but at least I have it here now. I will send this, I think, and good. This to the side. Send it. Yeah, I think. Any specific reason you want to look at C? Yeah, I'm looking at C mostly because C programs are faster, and usually older software is made in C. I will be looking at Windows now after I check out this table now, after we analyze it, but yeah. C is a fast language, it's pretty old, but it can be developed still. It will work decently, and we all will have what we need. Yeah. Mostly I like C because I can easily compile it for any system, since Linux and Mac already have GCC compilers inside them, and Windows is getting a bash terminal in some time this year, I hope, and for that we will be able to use GCC there as well. So GCC integrated makes everything easier for developers as well, and it's nice because C programs have a lot, and I mean a lot less things around memory layouts that they do. C programs also compile way better into ASCII and ASCII assembler and machine code, so they are pretty small. They're easy to transport, easier for me to send to you guys any software I develop and reverse engineer on that. So yeah, that's it. Low level, like embedded software, close to hardware for what they're here. Yeah, C is used a lot in low level hardware. If I'm not mistaken, drivers are developed in C as well, and those can get pretty complicated. But yeah, mostly C is used nowadays for low level. But if you want performance and also want to have a small size, it's that you want when working with embedded software, then you go for C. Assembler would be better for those kind of things, but it's so low level that it becomes too cumbersome to do anything. Assembler, I don't think, has functions in its implementation, at least the original one. You have jumps, you have go-tos, and a lot of stuff like that. No, you have jumps, you have push, you have get, and so on. So you can get stuff from memory, you can put stuff in memory, you can process, send to registers, add, subtract, and so on. But it's way harder to develop in and mostly used only for reverse engineering nowadays. I will be looking into assembler in a few streams because of the reverse engineering and all of that. Okay, let's get back into this. Okay, this one, understanding memory layouts, yeah, blah blah blah. So we have charbit, max, min, max, min. Okay, here's a code that will print the minimum and maximum and the bit, charbit 8. Yeah, I'm not sure why they did that. Okay, so here we have floating point types. Oh, we have those as well. Yeah, let me cut this over as well. Is this here, this corner? So we have something nice. Okay, so we have floating point types and integer types. I think that's how they are called. Integer types, yeah. So characters, letters from the ASCII table, integers, and longs are long integers. We have short as well for smaller integers. Usually an integer in C will occupy the 4 bytes in memory, since it can become a long. Unless it is static, then it probably will be a short if it's small. I don't know how the optimization is done. Yeah. Also for the float types, we have float, double, and long double. That's more for precision that we use them. 6, 15, and 19 decimal places. I think that 19 decimal places is more than enough for everything I will need at least. So yeah. Okay, let me see anything else here. The void type, that no variable is available. Function returns, function argument, and pointers as void. Okay, so nothing much here. Okay, let's close this up and start looking at Linux, because I prefer Linux. Okay, a big explanation here. Let me actually recover that tutorial point here. I need a notepad. Oh, come on. Notepad. Okay, I will be posting all links in the future in the Discord, so you can access them if you want for your own use, and so that people get their credits where they're due. Okay, this one is pretty big. Okay, I probably won't be able to go into Windows today, but yeah, who cares about Windows, right? Just kidding. Okay. In the first part of this Linux process series of article, we build up the understanding of Linux process by discussing about the main function, environment related C functions. Okay, memory, layout of process, if we try to visualize memory layout of process, we have something like this. Okay, it's exactly the same as C. So everything we have done for C is usable in Linux, since mostly it should stay the same. Command line arguments at the top, stack, heap, the BSS, the global data that was initialized, and the code. Yeah, process terminating functions. Okay. So let's do a quick recap since I'm already finishing here. Anyway, let me select everything in this here and pull it down. I will be posting this as well, so you can use it if you want. That will, come on, right down there. Okay, C and Linux memory layout. Okay, here. Okay, so we have the memory layout for C and Linux that is practically the same. Mostly this should stay the same. It changes depending on how we look at things. Here we have some differences in Windows. We have some memory mapping segment, and that's it. And the kernel space up top, that is for the entire system, not just a process. Probably I will look later into the Linux whole thing as well, so we know. But yeah, okay. This is actually a super user thing. Yeah, I will check this in another stream. Okay, here we have this executable code at the lower address. Then we go to initialize global and static data. These can be read-only when it is static, when it is a constant, and it will be read-write when it is a normal variable that can be altered. We have the block started by symbol, the BSS, that contains all uninitialized global and static data. These will be initialized with 0 when the code starts, when the code executes. These ones are done so that we have a separate section for what we will be altering during the flow and what we will mostly have initialized already, what we have not set to 0. So, and then the BSS will contain all variables set to 0 or that were not explicitly initialized. Those start at 0 as well. We have the heap that is mostly used for memory allocation. This is used by all shared libraries and dynamically loaded modules. So we have a piece of code that is loaded only if it's needed, or a library that is shared across all our process. These will be loaded into the heap. We have the stack that is a data structure that where the last in is the first out. So the first in is the last out. It's like a stack of coins. The first one you put there, as you add more coins to it, always the last coin is the easiest to remove, and that's how it works. And on the very top we have the command line arguments and environment variables. Also, the stack, we have the stack frame, that is a set of values pushed to the stack for one function call. We have the stack pointer, that is a pointer to the address on the top of the stack, because that can change a lot and so on. And garbage collection is kind of weird, so you could have the stack keep what's there and not clean it off, but just move the pointer so it's faster. Then we have what's saved on the stack. Automatic variables, colors, environment, like machine registers and some other data, and the return address. This return address is the minimum thing that is added on a stack frame. So, if we can somehow overwrite this return address, we can go back to whatever function we want to go. Okay, then we check the types and how much they weigh in memory. So we have chars with 1 byte, ints with 2 or 4 bytes, depending on if they are short or long. We have the floats and the doubles and the long doubles, each one with 4, 8, and 10 bytes of space respectively. So we can use those to calculate, for example, a string containing hello will have 5 bytes, and a double, even if it's 1, will contain 8 bytes in memory. So we can use this to know exactly where something is. For example, we know where the double ends, we can calculate exactly where it started. That is useful sometimes, not always, but that allows us to check memory and massage it maybe somehow, not sure. As I am starting all of this again, I don't want to make any assumptions that I know, because I probably am wrong on this. So, this should be it for today. I will be leaving now the stream. Sorry for the low quality, as always. The dropped frames are killing me. I can't get a better internet. It's too expensive here in Brazil, and my provider isn't as stable as I would like. Also, yeah, if you have any questions, put them in. I can stay here a bit longer and see what your questions are. Oh, if they were good for you, great. I dropped 837. It's nothing compared to usual. I usually drop 3,000 to 7,000 frames a stream, but since it was mostly static images, it shouldn't have affected that much anyway. But yeah, if you want, follow the channel for updates on Twitch. Also, if you haven't yet, join the Discord, follow me on Twitter for future things. I will be posting this diagram here I have on the Discord and answering there any questions. So, have a good day. I'm ending the stream now. Any questions you can leave for me on the Discord. We see each other again and at Tuesday if you can join. If not, it's okay. And yeah, that's it. I will stay a bit more, around another 3 minutes or something like that, if you have any questions. But yeah, that should be it then. Bye. Okay.